variation of the induction through a moving circuit. 47. A third method of arriving at equation 13 is by considering the rate of change of the amount of induction through a moving circuit. We need not think of a conducting circuit, but more generally of any circuit. Let it be moving in any way whatever, changing in shape and size arbitrarily. The induction through it is altering in two entirely distinct ways. First, there is the magnetic current before considered, due to the time variation of the induction, so that if the circuit were at rest in its momentary position, we should have the second law of circuitation true in its primitive form. Minus curl E equals G, when expressed for a unit circuit. But now, in addition, the motion of the elements of the circuit in the magnetic field causes, independently of the time variation of the field, additional induction to pass through the circuit. Let its rate of increase due to this cause be small g per unit area. If then, we assume that the circuitation of the electric force E of the flux equals the rate of decrease of the induction through the circuit always, whether it be at rest or in motion, the equation 14 becomes altered to minus curl E equals large G plus small g, where the additional small g may be regarded as a fictitious magnetic current. That it is also expressible as the curl of a vector is obvious, because it depends upon the velocity of each part of the circuit, and is therefore a line integral. Examination in detail shows that G equals minus curl vector product QB. So that we have, by inserting 16 in 15, curl bracket E equals G, the standard form of the second law of circuitation, when we use 13 to express the impressed force. The method by which Maxwell deduced 13 is substantially the same in principle. He, however, makes use of an auxiliary function, the vector potential of the electric current, and this rather complicates the matter, especially as regards the physical meaning of the process. It is always desirable when possible to keep as near as one can to first principles. The above may, without any formal change, be applied to the case of assumed magnetic conductivity, when G involves dissipation of energy. The auxiliary G in 15, depending merely upon the motion of the circuit across the induction, does not itself involve dissipation. Modification. Circuit fixed. Induction moving equivalently. 48. Perhaps the matter may be put in a somewhat clearer light by converting the case of a moving circuit into that of a circuit at rest, and then employing the law of circuitation in its primitive form. The moving circuit has at any instant a definite position. Imagine it to be momentarily fixed in that position, by stopping the motion of its parts. In order that the relation of the circuit to the induction should be the same as when it was moving, we must now communicate momentarily to the lines of induction the identically opposite motion to the abolished motion of the part of the circuit they touch. We now get equation 15, on the understanding that small g means the additional magnetic current through a fixed circuit due to a given motion of the lines of induction across its boundary, such motion being the negative of the abolished motion of the circuit. The matter is, therefore, simplified in treatment. For, in the former way, the process of demonstrating equation 15, which I have referred to as an examination in detail, is really considerably complex, involving the translation, rotation, and distortion of an elementary circuit, or equivalently for any circuit. Fixing the circuit does away with this, and we have merely to examine what happens at a single element of the circuit, as induction sweeps across it, in increasing the induction through the circuit, and then apply the resulting formula to every element. In the consideration of a single element, it is immaterial what the shape of the circuit may be. It may, therefore, be chosen to be a unit square in the plane of the paper, one of whose sides, AB, is the element of unit length. Now, suppose the induction at AB is perpendicular to the plane of the paper, directed downwards, and that it moves from right to left perpendicularly across AB. Let also from A to B be the positive sense in the circuit. It is evident, without any argumentation, that the directions chosen for Q and B are the most favorable ones possible for increasing the induction through the circuit, and that the rate of its increase, so far as AB alone is concerned, is simply QB, the product of the tensors of the velocity Q of transverse motion and of the induction B. Further, if the velocity Q be not wholly transverse to B as described, but still be wholly transverse to AB, we must take, instead of Q, the effective transverse component Q sine of theta. if theta be the angle between Q and B, making our result to be QB sine of theta. Now, this is the tensor of vector product QB, whose direction is from A to B. The motional electric force in the element AB is therefore from B to A, and is vector product BQ. Because it is the negative circuitation which measures the magnetic current through a circuit. Lastly, if the motion of B be not wholly transverse to AB, we must further multiply by the cosine of the angle between vector product BQ and the element AB. This merely amounts to taking the effective part of vector product BQ along the circuit. So, finally, we see that vector product BQ fully represents the impressed electric force per unit length in AB when it is fixed, and the induction moves across it, or that it's negative. Small e equals vector product QB represents the motional electric force when it is the element AB that moves with velocity q through the induction B. Now, apply the process of circuitation, and we see that small e is such that its curl represents the rate of increase of induction through the unit circuit due to the motion alone. This may seem rather labored, but is perhaps quite as much to the point as a complete analytical demonstration, where one may get lost in the maze of differential coefficients, and have some difficulty in interpreting the analytical steps electromagnetically. The fictitious motion of the induction above assumed has nothing to do with the real motion of the induction through the medium. If there be any, its effect is fully included in the term G, the real magnetic current. The motional magnetic force. 49. The motional magnetic force small h may be similarly deduced. First we have the primitive form of the first law of circuitation. Curl H equals J. When the unit circuit is at rest, where J is the complete electric current density, and next. Curl H equals J plus small j. When the circuit moves, where the auxiliary small j is a fictitious electric current equivalent to the increase of displacement through the circuit by its motion only. Next show that small j equals curl small h, and small h equals vector product dq. By similar reasoning to that concerning small e, so that by insertion in 19 the first law of circuitation is reduced to the standard form. Curl bracket h minus small h equals j, with the special form of the impressed force h stated. Comparing the form of small h with that of small e, we observe that there is a reversal of direction in the vector products, the flux being before the velocity in one and after it in the other. This arises from the opposite senses of circuitation of the electric and the magnetic force to represent the magnetic and electric currents. The magnetoelectric force. 50. The activity of the motional small letter h is found by multiplying it by the magnetic current, and is, therefore, small h times g equals g vector product dq equals q vector product gd. By the same transformation as from 11 to 12. We conclude that vector product GED is an impressed mechanical force per unit volume, and therefore, that vector product DG is a mechanical force, that is, of the Newtonian type, arising from the electric stress. By analogy with the electromagnetic force, it may be termed the magnetoelectric force, acting on dielectrics supporting displacement when the induction varies with the time. Of this more hereafter. Electrification and its magnetic analog. Definition of divergence. 51. So far nothing has been laid down about electrification. But the laws of circuitation cannot be completed without including electrification and its suggested magnetic analog. Describe a closed surface in a dielectric, and observe the net amount of displacement leaving it. This, of course, means the excess of the quantity leaving over that entering it. If the net amount be zero, there is no electrification within the region bounded by the surface. If the amount be finite, there is just that amount of electrification in the region. This is independent altogether of its distribution within the region, and of the size and shape of the region. More formally, the surface integral of the displacement leaving any closed surface measures the electrification within it. This being general, if we wish to find the distribution of electrification, we must break up the region into smaller regions, and in the same manner determine the electrifications in them. Carrying this on down to the infinitely small unit volume, we, by the same process of surface integration, find the volume density of the electrification. It is then called the divergence of the displacement. That is, in general, the divergence of any flux is the amount of the flux leaving the unit volume. and in particular, the divergence of the displacement measures the density of electrification. Similarly, the divergence of the induction measures the magnification, if there is any to measure, which is a very doubtful matter indeed. There is no evidence that the flux induction has any divergence. It is purely a circuital flux, so far as is certainly known, and this is most intimately connected with the other missing link in a symmetrical electromagnetic scheme: the unknown magnetic conductivity. Divergence is represented by div, thus div d equals rho, div b equals sigma. If rho and sigma are the electrification and magnification densities respectively. In another form, electrification is the source of displacement, and magnification the source of induction. How these fluxes are distributed after leaving their sources is a perfectly indifferent matter, so far as concerns the measure of the strength of the sources. In an isotropic uniform medium at rest, the fluxes naturally spread out uniformly and radially from point sources of displacement, or of induction. The density of the fluxes then varies as the inverse square of the distance, because the concentric spherical surfaces through which they pass vary in area directly as the square of the distance. Thus, d equals rho over 4 pi times r squared, and b equals sigma over 4 pi times r squared, are the tensors of the displacement, and induction at distance are from point sources rho and sigma. If the source be spread uniformly over a plane in a uniform isotropic medium to surface density rho or sigma, then, by the mere symmetry, we see that half the flux goes one way and half the other, perpendicularly to the plane, so that d equals half rho and b equals half sigma, at any distance from the plane. But if we by any means make the source and all the flux one way only, then d equals sigma, b equals sigma, at any distance.